Welcome all. A very warm good evening to everyone. The need for more and better education for students in STEM, science, technology, engineering, and mathematics fields have been nationally proclaimed in the countries for years. This process has led to change the way the physics is taught in high schools to hands-on discussion-oriented methods. We have with us Mrs. Meera Chandrasekhar, an alumna of our institute who is also a distinguished alumnus awardee of IIT Madras. She did BSc in mathematics at Mysore University and BSc in physics at MGM College in 1968. She did a MSc in physics at IIT Madras in 1970 and PhD in physics at Brown University. She was also a research associate with Professor Manuel Cordona at Max Planck University. She served at the Physics and Astronomy Department, University of Missouri, Columbia in various positions. She started as an assistant professor and a research associate in 1978. Then she became an associate professor in 1986 and professor in 1988. She was a Curators teaching professor in 2004. She also served as a professor in Baylor University. Right from her childhood, she was very much interested in studies. She was also a recipient of National Talent Search Examination Scholarship sponsored by Government of India. IIT Madras awarded her bronze medal and certificate of merit for her first rank in MSc class. The University of Missouri facilitated her with Purple Chalk Award for excellence in teaching, Chancellor's Award for outstanding research, William T. Kemper Fellowship for Teaching Excellence, President's Award for outstanding teaching. She has membership in professional societies like American Physical Society, National Science of Teachers Association, American Association for Advancement of Science, etc. She published around 130 papers and gave a lot of presentations based on her research work. May I now invite Mrs. Meera to come on the dais and address our students.
Thank you very much for inviting me here. I believe this is a talk that is in the G. Lakshmi Memorial Lecture Series, if I'm not mistaken, and in honor of G. Lakshmi, who was one of the first female students to get a PhD in physics at IIT Madras. I'm very honored to be part of this lecture series. I knew G. Lakshmi when I first came to IIT Madras. So I came here as an MSc student in 1968. At that point, G. Lakshmi had just finished her master's degree, and she had joined the PhD program. So she was one of the first research scholars I got to meet during that time. It was very interesting for all of us to be in IIT, as you can imagine, at that time. Before we got here in 1968, there were 7 female students all across campus. This adds up the numbers of 3 or 2 in the BTech program, and the rest of them in various PhD programs in chemistry, physics, and math. So at that point, I think the 7 students got fed up of living in faculty quarters, and they decided that they would petition the director to build a hostel for them. So a hostel was built, and they figured, for about 5 or 6 years now, we've only had 5 or 6 students. We'll build a women's hostel with 24 rooms, and we'll be set for the next decade. Well, the moment they built that hostel, the word must have gotten around, because there were 22 students that very first year when the hostel opened, and so the hostel was full the moment it was opened. And I was part of that cohort that came in. So the research students, G. Lakshmi included, were a great inspiration to all of us, because many of us did not know what research was. We really didn't know what a PhD meant. We kind of knew what an MSc meant. It was more classes just like BSc. But the introduction to the whole process of doing research and what it took for a person to conduct research and stay in research was something I think people like Lakshmi taught us. My most enduring memory of her is of her carrying around a whole bunch of punch cards of a Fortran program. She had this box she would lug around. The reason she would lug them around is because there was no computer at IIT at that time that could run those programs. So she would have to construct the program, make up these punch cards, and then ship off the box to TIFR, where they would run the program. And a week later, she would get the response back and the punch cards back saying, job failed. And it was usually due to a misplaced space or a command line or something like that. And so she'd go through and fix it all up, send it back again. And so this process continued, as you can imagine. You know, a big stack of cards like that, you're bound to make a few mistakes. So at the end of it, of course, it all worked out, and she did graduate and get a PhD, had several publications. A couple of weeks ago, before I left the US to come here, I called Lakshmi's husband, who lives in Oregon, and I told him the story. And he just laughed when he heard the story. He says, well, let me tell you the follow-up to that story. About 10 years later, Lakshmi was working at Wang Labs in Boston. And as she joined the company, the supervisor set her to work on this computer program that a previous employee had been struggling with for a whole year. So Lakshmi got to work on it, and a week later she was done, and the program was working. And she took it back to the supervisor and said, here you are, it's done, now give me another project. And he looked at her and he said, how did you do that? You know, how did you get to debug the thing that that guy had been struggling with for a whole year? And she said, oh, well, that's the secret. Well, the secret was that this whole process that she had gone through of sending the box of cards to TIFR and getting them back had made her an expert on all the debug codes. She knew exactly what each one of them said and exactly what you had to do to fix it. So she could make multiple fixes in one run, which probably nobody else could do because they'd have to look up all these numbers and codes and stuff like that. So it stood her good stead. And of course, Lakshmi then went on to have a long career in the telecommunications industry, as it turned out. She worked at many different places. One of her passions, all through the last couple of 3 decades of her career, was to work with young students. She was very interested in mentoring young students and teaching them physics, math, science, whatever it was that they needed to be taught. She volunteered in various school districts and libraries in many places that she lived in the US. And that she felt was one of the big contributions that she had made in her life, in addition to being a good scientist. So what I'd like to do is to sort of take that thought forward and tell you a little bit about some of the work I've been doing in education and in mentoring of younger students. I have, of course, I am, of course, a scientist, a practicing scientist even now, but I've sort of led a dual life for the last 20 years, where I've had a research career and in parallel a career that involved education. So today I will tell you a few of the things that I worked on along with several of my colleagues, and also tell you a little bit about what I consider the path that the methods of education should take in the sciences. Okay, so now let's see hopefully this machine will work too. I don't know, how many of you here are in the social sciences? Not too many of you, but you know, one says that mathematics is sort of the basis of everything, but when it comes to understanding a lot of the ideas out on this side of the image, such as physics, chemistry, biology, and so on, math is really important. It turns out to be the thing that helps us understand very deep thoughts. It also turns out to be one of the things that is a stumbling block for a lot of students as they start to learn various physical sciences or even the natural sciences. So what I'm going to do today is to tell you about the kinds of perceptions that people have just because you say you're a physicist, or I'm sure this happens to mathematicians too. Just as a teaser, I will tell you that some of the work that we've done in the state of Missouri, which is where I live, has helped us increase or double the number of students who take physics in high school. And this has happened over a period of about 10 years. Now, the system of education in the US and in India are somewhat different. And so the kinds of things I'll be saying, some of the school district stuff I'll be saying really is based on my familiarity with the US system. In the US, students need to take 2 science classes in order to graduate from high school. And the way they're set up as year-long courses. So in 9th grade, you take 1 science, whatever it is that your school says that is the right thing for you. Sometimes it's general science, sometimes it's physical science, sometimes it's physics. You know, it's whatever it is that the school decided was the right thing for those 9th graders. They don't have much of a choice. In 10th grade, in 11th grade, and 12th grade, through the rest of high school, they get to choose what science classes they take. There is no requirement that they take this, that, or the other course. So most students take biology in 10th grade, and then they take chemistry in 11th grade, and really they're done, right? They've taken their 2 or 3 science courses. They never have to take physics. So the result of all of this is that only about 36% of students in the US take physics in high school. And what that does, of course, take any kind of physics, okay, beyond 6th or 7th grade. So what that does is it places them all at a disadvantage when they come to college and they say, I'd like to do engineering. Well, you know, it's a heavy lift. If you've never done physics in your life, and now you want to go take a calculus-based physics course in college for the first time in your life, that just doesn't work very well. So basically, 64% of students are disadvantaging themselves from careers in science when they don't take physics. So the big push then was to see how we could change this whole attitude. And the result of that then was over this 10-year period of this doubling of students taking physics. So why is this? Of course, everyone has their own theories, and I have mine. So one of my theories is that it has to do with the perceptions of physics. Kids think that this is what physics is. Spaceships, crazy scientists, robots with armies and guns and lasers, preferably wearing lab coats, okay? I've never worn a lab coat in my whole life, but that's what kids think physics is. Teenagers think this is what physics is. How many of you recognize this picture? Ah, there we go. Okay, so they think physicists are all a bunch of geeks. They have no fashion sense. They all wear glasses, okay? So that's what they think physics is. Undergrads think this is what physics is. Okay, bunch of Greek-flavored mantras that you kind of invoke, preferably to pass the class with a good grade. Okay, who cares what it really means? It just needs to work. Well, you can see that I don't like that idea. This is what I think physics is as a physicist. And that laser is not aimed at any aliens. So we've all got completely different perceptions of what physics is. And if I were a chemist standing over here, I could probably tell you similar stories of what people think chemistry is and so on. So there's a major perception problem here about whether one should take physics, when one should take physics, does it make sense to take it? So there's a lot of pushback from the parents. There's a lot of pushback from school administrators, and sometimes from the kids themselves. So these are the kinds of things one needs to overcome if one is to make a subject like physics palatable to the general public. So about 20 years ago, I met the science coordinator of the school district in my hometown, Columbia, Missouri, and she and I came up with a plan of creating some after-school programs for younger students. So, of course, when we thought of younger students, we said, hey, you know what? We should really go with what our passion is, which is to create the programs for female students. And of course, for me, this is personal. If one looks at the PhD recipients, and this is the US, these are the US numbers, one can see that the number of PhDs in the life sciences has gone up from about 45% all the way to about 70% of the life sciences. And the physical sciences is somewhere from about 35% to about 60%, which sounds pretty good until you look at the specific numbers by field. By field, physics is out here at the bottom of the heap. It started out with about 3% in the 1970s, and now is up to a very disrespectful, I would say, 19%. It's taken 30 years to get from 3% to 19%. So there's not a whole lot of things for us to be proud of. But that's what the statistics are. So this perception problem kind of feeds into a whole different aspect, of course, in the career issues too. So our plan then was to see if we can affect some of these numbers, at least affect the perceptions. So we created a series of different programs. The first was called Exploring Physics, and this is a program for students in 4th through 6th grades. It was a hands-on program, mostly made to be kind of fun. And you know, I just realized that that man sitting over there is actually my husband. Somehow he must have been visiting us that day, and so he got to be in the picture. The second, after we finished the 4th through 6th grade program, we went on to another program which was called Families Exploring Science and Technology, and this was for 6th and 7th grade students. And in this program, students constructed whoops, where did I go? Okay. They constructed a drawbridge, a moving drawbridge with gears and an electrical motor and so on. So it included some mechanical engineering and electrical engineering concepts. For the slightly older students in 8th and 9th grade, we had a program called Saturday Science, which brought in people from various city industries, including people who could work with robots, the fire department, and so on. For even older students who were in 10th and 11th grade, we had a residential program where the students built a factory where they produced polymer balls. So again, this program included various science and engineering concepts. Now, there were a couple of graduate students who did their PhD thesis work based on the Newton Academy. And their idea was to see whether programs such as this affect students' perceptions of what kinds of careers they can go into. And what they found was similar to the findings from other studies, which is that it is important to have such programs to make students aware of these different content areas and different careers. But in order to truly make the step into going into that career, one needed to have really high level and really good quality classes in the schools, because that's where they got the long-term impact. So it was pretty clear that we needed to start impacting the classrooms in the state, preferably to learn more physics and to learn it in a more interesting fashion. So in parallel with this time frame and beyond that, we started working on teacher programs, teacher development programs, so that they could offer some of these courses in high school. And this, for example, is sort of the same graph that I was talking about before, where only about 36% of students take physics. So the question was, what exactly should we do in order to introduce more physics to high school students? It turned out that about 10 years ago, there was a move within the state, and it was important that there was a move from the teachers in the state and the districts within the state. The move was to try and introduce physics earlier in high school, which is to introduce it as a 9th grade course for a whole year as a conceptual physics course. The background for that comes from the way the courses are structured in the US. Back in 1893, and that is not a typographical error, back in 1893, there was a group called the Committee of 10, and they set up what the syllabus for different classes needed to be in the American school system. And that's been borrowed into many other school systems across the world. Their idea was that since biology at that time was mostly a descriptive science, that it should be taught first. I mean, mostly people drew pictures of plants and animals. Chemistry was really just a bunch of experimental procedures. Remember that the model of the atom had not been written at that point yet. That only came in 1905. So chemistry would come second, and physics, being the most mathematical, was postponed to the very end, to 12th grade. But in the intervening 120 years, a lot has changed in biology and a lot has changed in chemistry. In fact, biology is by far one of the most complex subjects. If you want to learn about DNA, then you need ideas from chemistry, you need ideas from physics, you need to know about energy transfers and so on. And so really, to understand biological concepts, one needs to know a lot of chemistry concepts. And to understand a lot of chemistry concepts, especially to do with energy transfers and so on, you need to know physics. So really, the more natural way in which one needs to study these three subjects is to take physics before you take chemistry and biology. So this movement, which was called Physics First, came about 20 years ago. It was pushed forward by a Nobel Prize winner, Leon Lederman. And his suggestion was that physics be taught at a conceptual level, not as a mathematical course as it is in 12th grade, but really taught on a more conceptual level, taught more hands-on. And so that a lot of those concepts then can be used to build into the chemistry and the biology courses. So that means then that one needs to teach physics in possibly a different way. And some of my work then started moving towards teaching physics in a different way, but also teaching it at more levels so that the schools could then implement some of this content into their classes. So I teach, I've taught two different levels of courses. One is for elementary education majors, so they teach 0 through 5th grade. And then the other effort that I put forward was to work with a whole group of collaborators within my university and from the school districts to train teachers to teach physics in 9th grade. So physics in 9th grade then cannot look like that. It really has to look different because students are not ready for that, okay? So how does one do it? Well, what one needs to do is to make it much more hands-on, much more relevant to the kinds of things students are used to, maybe based on toys that they have played with, and certainly something where students not only work with the materials, but also use the observations from the little activities that they have performed to come up with the concepts. So this is to be done in a fairly well-planned fashion. If you just throw toys out there and say, hey, here's some cool stuff, you know, see what you can learn from it. Well, students will just play with it, and they probably won't learn anything from it. So it's really got to be done in a more deliberate fashion. So one has to go through a process of saying, okay, so you looked at this stuff, which are a couple of wind-up toys. What do you expect them to do? What kinds of energy do you think are involved in these wind-up toys? Then you let them play with the wind-up toys so that while they are playing, they're thinking about your questions. If you just give them the toys and say, play with this and tell me what you saw, then they probably will never go to that analytical frame of mind where they're trying to figure out what's really happening in this machine, other than breaking it apart or something like that. So this kind of methodology is something that's called the modeling methodology or the modeling pedagogy. This pedagogy was put forward by David Hestenes and several of his collaborators. This particular reference I have is from 2008, but his first papers probably came out in the mid-1990s or the late 1990s. So the modeling pedagogy has basically two phases. It's got the model construction phase and the model deployment phase. So let me tell you what we mean by this stuff. Well, what we mean here is that if we are going to talk about, let's say, accelerated motion, okay, the standard way in which a accelerated motion will be taught in class is that the teacher will be standing here at the blackboard and writing possibly on the blackboard or maybe showing slides. He or she will say, okay, you know, cars don't always go at the same speed. They sometimes slow down, they sometimes speed up. And here is the equation that you need to use in order to figure out how they slow down and how they speed up. And by the way, this is the equation for velocity when you have accelerated motion. Here's another equation. This is for displacement or the distance traveled. And okay, so now you've learned it all. Here are some problems, go do them. And then students do the problems. And so at the end of it all, the student feels good that he's done the problem, pats himself on the back or herself on the back. And then the professor feels good because everybody got 80% in the exam. But here's the real problem. This is fine for somewhat simpler stuff. As you keep going deeper and deeper into the concepts, the question is, how much conceptualization has the student done about the concept? And what we found is that the answer is not much. So if you employ certain tests that really understand the conceptual understanding of students, it turns out that their conceptual understanding when they have a standard lecture course is really not that good. The second thing that is not that great is that if you go back 2 years later and you give the same student that same physics final exam, what kind of results do you think you'll get? Probably not very good ones. You probably won't get an average of 75% like you got the first time around. So the retention is also somewhat lower. So the whole idea of the modeling pedagogy then is to have students work with materials, discuss what's going on, and create conceptual models of the concepts. So they are the ones who are, in a sense, constructing their own knowledge by constructing the concept themselves. Then they conduct an experiment and check on their conceptual model. And then they analyze the experiment and then produce from the experiment itself the formula that describes the experiment. Okay? So no formulae are given to the student when you're using this methodology. The students are actually producing all these formulae themselves by doing a hands-on activity, an experiment, doing the analysis. And then once you do that part of the model construction, this is the 3 phases that I just described for you. Okay? After they do the model construction, then you go into the next phase, which is you go deeper into the understanding of the concept. Because at some point, you can't just be doing it all hands-on. You do have to do it mathematically. You do have to do calculations. And that is the phase that is called the model deployment. Okay? So one does one comes up with an idea, constructs the model, and then you go through and do practice problems. Maybe you do a reading because not every concept can be addressed with a hands-on experiment. If you want to know about Coulomb's law, at some point you really have to talk about charges and you can't be holding them in your hands. So there's got to be some reading involved and perhaps an application lab. Okay, so this is sort of the general methodology of this modeling pedagogy. How does the class look? Well, the class looks kind of different. There is no professor or teacher standing out in the front with a blackboard. A lot of stuff is done hands-on. This, by the way, are pictures from our Teacher Institute. In case you're wondering why these 9th grade students look so old, they're actually the teachers. So in the pre-lab discussion phase then, they activate their previous knowledge, make mistakes, make wrong predictions, it's fine. You get to check them all out. Then they design the lab experiment, and by saying design the lab experiment, I really should stress that word. Lab procedures are not given to the students. They are asked, what kinds of things do you think you can measure when you look at this stuff? You've seen maybe a ball rolling down a ramp. What kind of measurements can you do? So the student has to come up with lab procedures on what they're going to measure and how they're going to measure it. the teacher is always there. So the role of the teacher here is not to stand there and provide answers, but to really sort of oil the discussion, if you like. There's a lot of discussion that goes on in these classes between the students. There's a lot of talking. It's a loud class, but they're all talking science. Okay, they're not talking about other stuff. And then after they conduct the experiment, of course, then they analyze the experiment to come up with the model for the concept. So this, for example, might be, you might find that the student has a conceptual model. That is one possibility. Or they might have a mathematical model. So you might actually come up with a formula at the end of this process. Okay, so now the class involves a lot of group work, a lot of hands-on labs, and a process that we call whiteboarding. Somehow the G got cut off from that caption over there. By whiteboarding, what we mean is the use of these small whiteboards where you write with a dry erase marker. A lot of questions are discussed within the class using whiteboards. So a student might, the teacher might pose a question. Students think about what do I think the answer might be, and they might write that down in their notebook. Then they talk to the other two people sitting at the table with them, and they come to a consensus on what they think the answer might be to that question. And then every group in the class gets to present what they think is the correct answer. So this way, the whole class is involved in a discussion of what the concept might be. Okay, another technique that is used a lot in the modeling pedagogy is what is called multiple representations. So when you see a formula like this, and most of you probably here are engineers or physicists or something like that, you pretty much know everything that's happened. You can think of all different possibilities of what this formula means. But for a young student, this formula really doesn't mean very much. It's just some stuff that the teacher gave me, and this is how I use it. So in order to understand what this concept or this idea means, one has to use more than one way of expressing the concept. And that's what we mean by multiple representations. So, for example, here's a verbal representation of this idea. I say I start from a point, maybe some point x equals 0, and then I move in the positive x direction and a constant velocity with no acceleration. So that's really saying this in words. Or we might draw a picture where you show this object at equally spaced intervals of time. You might draw the actual picture itself, or you might draw a motion diagram with little spots and the arrows to show the velocity. And so this is really representing this idea in pictures. And this kind of thing works well for students who've really not had a whole lot of math. They understand the concept well, but maybe not the way to express it mathematically. And then here, of course, is the third possible way of representing it, which is through the use of graphs. Okay? So verbal, pictorial, graphical, mathematical, you can have 4 different representations. And really, one needs to know how to move between the representations quite well in order to really understand the concept well. Okay, so now, I didn't know how many of you were going to be here, and so I did not come prepared with hands-on materials. I kind of like to do this so that you yourselves are doing the experiment, but that just was not feasible. So I'm going to have to do a slightly shortcut method of showing you how we construct a model, because I want you all to try constructing a model too. So what we'll do is we'll do a kind of a version of a pre-lab discussion, okay? And in this pre-lab discussion, imagine that you are a 13-year-old. Think of yourself as the 13-year-old, or perhaps a sister, a child, nephew, niece, whatever, who is 13 years old, who's probably not learned about electrical circuits yet, okay? And so what we're going to do is we're going to say, all right, if I gave you one bulb, one battery, and one wire, how would I connect up these 3 elements to make two kinds of circuits. One circuit which does not work, where the bulb does not light up, and the second circuit where the bulb does light up. Okay? Two different circuits. So here's what I want you all to do. I want you to talk to your neighbor for a couple of minutes and come up with some ideas of what kinds of things this 13-year-old person might say. Okay, talk to each other. Okay, so now I'm going to show you. So if you were in my class, you would right now have a whiteboard, okay, and you would be drawing pictures. And then after a little while, I'd ask you to talk to people around you perhaps. And then I'd call on some people to come up here and show their whiteboards. You have to imagine all of this, okay? You show your whiteboard and you explain to everybody why this circuit that I drew is a circuit that won't work, and why that second circuit that I drew would be a circuit that will work, okay? So you have to go through this process of explaining. And as you can imagine, in a class like this, students will come up with some pretty crazy ideas. Many of them will come up with completely wrong ideas that they think will work, all right? Now, what does a teacher do in such a situation? It is really important at this pre-lab discussion stage for the teacher not to say, wrong, right. You don't say that at all. You just say, oh, okay, so explain to me why you thought that. So you let all ideas come forward. You do not come to a conclusion at that point, okay? What you do is, after you have come you've come up with all the pictures, you draw all these pictures on the board. This is what I do. I draw all those pictures on the board and say, okay, these are all the circuits that we're going to test. Because a few minutes later, I'm going to give everybody one wire, one battery, and one bulb in my class. I give them all this stuff, and then they get to test out the pictures that they drew and figure out which ones work and which ones don't work. And very often, of course, we'll come and say, oh my gosh, I came up with completely the wrong idea. So we have to allow the students to make the mistakes, because that's how they'll know that that was a mistake. You don't want them to see the mistake for the first time in the test. You really want them to have done it already and moved past that. So I'm going to show you some of the pictures that my students came up with. How many of you said this? Raise your hand. How many of you said that? Nobody said that? Thank you. There's always a few people who say that. Not possible. Give me a wire. Nah. All right. How many people said that a kid might draw a picture like this? Okay. Did you think that they thought it would work or not work? They thought it would work. They thought it would work because it's connected to the battery, right? I mean, it's like having a faucet. You turn on the tap and the water comes out. That's what the battery does. Of course, you know that that's not correct. Okay. How about this one? How many people thought of this picture? Well, if you had a piece of paper, you'd probably have thought of it. And most people that I ask, they say, oh no, this is not going to work. But you need to strip the wire. Like that. And then it'll work. Okay, how many people do you think would have thought that? Right? Okay, you'll be surprised how many folks, when I give them this hands-on activity, actually ask me for a wire stripper. And I usually give it to them and say, don't cut the wire, but do whatever else you like. And this is what they do. Okay. And then how about this one? This is a great favorite. This is a closed circuit, right? Will it work? Well, you all know that it won't work. I always have to remember I'm at an engineering institution. it's surprising how many times my students do this, and then, of course, their fingers get burned by the hot battery. And that teaches them a lesson that I could never teach otherwise. Okay, and here is another one, this one. Okay, you see I was getting away with this picture drawing thing. Okay, and then so after this, students actually try out all the designs, and they find that, of course, this is the one that works, right? And the reason, so the question is, why does it work? All right, and here's another one that works, okay? And it's important for students to realize that these two pictures both work, because sometimes students tend to think that the bulbs also have a positive and a negative. I did something. Can you all hear me if I talk loud? Or you need for me to be behind the podium? Yeah, okay, let's try this. Okay, I like to walk around, but fine, I'll stay here. So students very often think that the bulbs have a positive and a negative, and that's why it's important for them to try this one. And then, of course, there's a few more variations on this theme, which one can go through. And at the end of it all, so what is the whole point of this discussion? Because we've done this whole activity, what was it that we wanted students to understand at the end of it all? Thank you. Okay. What we wanted them to understand was that something flows. And this whole idea of something flows very often comes from the idea, from that one activity where they burned their finger on the battery by shorting it. Okay, that's the one that tells you something's happening over here, something's flowing, some energy is flowing, and that's what's making the battery hot. So this idea of something flowing, even though it's a microscopic idea, actually does come through in a macroscopic experiment. So this is what we want them to understand, that there's something that's flowing. We usually think of electrons flowing, and then, of course, in order for electrons to flow, we need to have a complete circuit. And this is what we mean by a complete circuit, not just any old stuff connected together in a circle. Other concepts that come out of this activity is that you need to have contact points. Every electrical device has at least 2 contact points, and the contact points have to be arranged, one after the other in order for the particular circuit to work. Furthermore, these contact points are made of metal. Okay, so the whole idea of insulators and conductors also comes out from this activity. So you see, from this very simple activity, one can connect to a large number of different concepts without necessarily having to do them in exactly the sequence that you will find in a physics textbook. Here's another thing that comes out of this activity, which is, why is it that only the filament glows in a light bulb and not the whole light bulb? There's only one little part of the light bulb that glows. And so that sort of brings you to the idea of, well, okay, so the filament must have some characteristics that are different from the guide wires that hold up the filament inside the light bulb. So these are sort of the initial activities that we do when we start our electrical circuits lesson. After this activity, we do a whole series of other activities where we look at series circuits and parallel circuits, and students measure voltages, they measure current, and they look at the brightness of the bulb, and they see how voltage gets distributed in series circuits and so on. So there's a whole bunch of different things that kind of follow after this experiment, all based on hands-on activities. And after many of these sort of grosser concepts or the macroscopic concepts have been learned, we start to talk about things that have to do with more materials or microscopic type of concepts. And that is one about the resistance or the, okay, So this is where I have to stop this. And excuse us for this little bit of, okay, now can you play the movie? And this, what you're going to see is a discussion in my classroom of students who were asked the question, what causes resistance? Come up with ideas of what causes resistance.
We said the type of light bulb.
The gender, then light bulb?
The type of material.
We said like if it was a conductor or insulator.
We said the size of the object.
We said like the wiring inside. Like some we've noticed have like fewer wires, but they're a little bit thicker wiring, or if they have a ton of the really small wiring inside of it.
We said the temperature, so like if it's hot or cold.
We said the number of electrons within a material.
Okay, so tell me a little bit more about that.
More electrons, more resistance.
I'm thinking kind of like in regards to a light bulb, maybe the gas on the inside.
We said the length of the wire.
They kind of said this, but we are thinking the diameter of the wire.
The diameter of
Because-
the wire.
Yeah, the path of the electrons would be.
Say that again.
The path of the electrons on like a bigger would be. Wouldn't you think it'd be harder? And
I don't know.
I don't know.
So you've got the diameter of the wire.
Yeah.
Okay. So you've got, let's say, a wire that's a big fat wire like that. You know.
Yeah.
And then you got a skinny little wire like that. So you want to take a guess about
Wouldn't
fat
it be
wire versus
slower?
skinny wire?
Wouldn't the electrons move slower on the fat wire and faster on the smooth?
Okay. But how would it affect the resistance?
Like if that wire, maybe because electrons bounce up and down, it'd be easier for stuff to pass through because it's not as compact and like the electrons are more spread out. Whereas like a little thin wire, they have a smaller space to bounce around in to move, so it'd be harder. And I don't know.
So you're basically saying that if you have a big fat wire, then the path of the electrons might not be as constricted. It's like having lots of lanes of traffic.
Yeah.
Whereas the skinny wire is just like having one lane going that way and one lane coming this way.
Yeah.
Be more
Okay, so
compact.
now, which way would the resistance go?
Like more resistance for a little wire.
More resistance for the skinny wire and
Yeah.
less resistance for the fat wire? What do you think, Bethany?
I have no idea.
I'm thinking. Yeah.
Okay, we're gonna figure it out, right? So these are just our educated guesses.
Okay, so now if you could return me to my PowerPoint. Okay, there we go. All right, I don't know, I hope you all could hear some of the discussion back there, but this particular discussion took about 20 minutes in the class, you know. So I took the movie and then I edited it down so I didn't have to subject you to the entire 20-minute discussion. But the part that you don't see me doing over there in the video is that every time somebody came up with an idea, I would write it down on the board, okay? So that it was all there for the students to discuss later and say, oh, this one really doesn't make sense, that one makes sense, and so on, okay? So all these ideas are up there with basically no commentary from me, the teacher, as to whether it is right or wrong. You just have to really take a very neutral tone because this is the initial guesses or the initial discussions that the students come up with. The next stage is to test these ideas, and they get to test the ideas. So in order to test the ideas, we have a couple of little boards that we've created. This particular one uses pencil leads. We use like 3 different kinds of pencil leads, an HB lead, a 6H lead, and a 2B lead or something like that. And then students actually measure the resistance as a function of length because that's one of the things they come up with. And then there's another board, and this is the kind of results that they get from it. So it's a really, you know, perfectly bona fide experiment, except it's done with much simpler looking materials. So from this then, students figure out that, oh, as length increases, resistance increases. And also that all materials don't have the basic fundamental resistance, which we call resistivity. If you have an HB lead, it has much less resistance per unit length than the 6H lead. And then there is a companion experiment where we measure the resistance as a function of diameter and then come up with all of those relationships between resistance and length, diameter, and resistivity. Okay, so I hope this gives you some sense of how the class might be structured when one uses this modeling pedagogy. This is the method that we have used to teach teachers, and as I said, a whole bunch of 53 districts across the state of Missouri have participated in this program. Missouri is not a very popular state. We have about 65,000 students graduating from high school any given year, and so now about 13,000 students are taking this class. The enrollment, therefore, has gone up over a series of years. In the initial stages, before our program started, there was only about between 10 or 11,000 students taking any physics class. After the program started, we had a huge increase in the numbers of students taking this 9th grade physics class, which is called Physics First. You can see that the latest numbers are approximately 17,000. And of course, what we wanted to know is of those 17,000, how many were students who, in districts that came to our program, which started in 06 and 09. And that is shown in this graph. The green bars show the numbers of students in the districts that came to our projects. You see that there are increases at certain specific times. Our first project started over here in 2006, and then there was a small increase and a level off. Second project started over here, and then it took 2 or 3 years for some more increase to occur, and that's what you're seeing up here. In the meantime, the students who are taking the regular 11th or 12th grade physics has stayed more or less a constant. From a nationwide perspective, this 9th grade physics is taken by about 84,000 students out of 1.4 million who take any physics class in the US any given year. And so therefore, about 15% of those students are from Missouri. And we make up only about 2% of the national population. So I think that's a pretty good place to be right now. And here are all my many collaborators over the many years. Projects such as this are not done by one person alone. They really require a whole team working together. And these are all the folks who have helped. Thank you.
Where they do labs, do they take that course by choice, or is it compulsory for the students?
So your question was, do they take the 9th grade physics course by choice, or is it compulsory? It's actually compulsory. And because whatever class is taught in 9th grade turns out to be the compulsory science course.
And do all the students show equal interest in working with their hands on the experiments?
Yeah, well, you know, not everybody takes to working with stuff that easily. What we found is, by and large, the teachers in the districts seem to really have a good feeling for the course. They feel like this is the way science should be taught. They've exported the methodology to other science classes as well. So there is really much more excitement in the class on the average when they take this hands-on course. Now, not every kid takes to it. There's always a few who say, give me that answer. Forget all this discussion. Okay. So yeah, there's going to be some variation. What the teachers do find, though, is that some of the students who are always the troublemakers in the class seem to really like this class, and they can keep them in check.
My question is, all this engagement with students in schools, how does it translate, if at all, to how they do in college? Do they choose physics more in college, or do they perform better when they get to the higher studies?
And that's the million-dollar question. We don't know the answer to that yet. That sort of involves a longitudinal study over several years. In fact, one of the things that we are doing at the University of Missouri this semester, and also in the next couple of next semesters, is to track some of the students and is to basically do surveys for the students who come to the university, because the University of Missouri captures about 10% of Missouri students. So that's a fairly large number from which one can draw some conclusions. And we are hoping to analyze some of that data to see what kind of effect that has had on their career choices.
Yeah, thanks for a nice talk. So my question is that what is your comment on the Indian schools, like where we have in one school in 9th or 10th standard, we have 160 students in one bench, there are 6 people are standing, and even in school we do not have like a proper theoretical class. So how do you demonstrate the physics experiment or biology or chemistry experiment? Because in school we do not have any like demonstration.
Right. And this, by the way, is a problem not only in India, it's a problem in the US as well, in the sense that these experiments, by the way, are not demonstrations, they're done by the students. So it adds an additional burden because now you need not just one set of equipment, you need 10 sets of equipment. So some of these pieces of equipment are fairly simple, they're not tremendously expensive, and I think those are the ones that surely get adopted more easily. One of the funny things we found was that all school districts would say, we don't have any money for equipment. And then what we do is we would give the teachers one set of equipment so they could use it in their classes. After the administrators saw how well those experiments worked in the classes, magically they found money for more equipment. So some of this is also a question of making sure that the value of the program is seen, so that they can, in fact, go out and try to find funding for the materials. It's usually not an immediate process. It takes 2 or 3 years, but we found that that's what has happened in our districts, many of which are very poor and rural as well.
The hands-on experiments to deeper formulae and equations.
For this, we asked this question of some of the teachers in the upper levels, like in the 10th grade, 11th grade, and so on, where they had some mix of experiments and theory. What they find is that the students who come out of this 9th grade class are really prepared to understand science and to think about stuff logically and to actually think. Okay, that was one of the big things. And also to engage in scientific discourse and discussion in the class. That was something they found that students previous to them had not done. And so that has really kind of increased the level of engagement in the classes, even though the classes might end up being more theoretical at that level.
Yeah, I had one question. You showed some figures about the enrollment of students in physics as your programs went on. But do you find that, compared between physics, chemistry, and biology, at the school enrollment level, that, is physics at some kind of a disadvantage today only because I have a feeling that, at least somebody who wants to do something in science would say, okay, excited by DNA, biology, bioengineering, biosciences. So do you feel that kind of a disadvantage in trying to push physics ahead of the others?
Okay, so some of this issue of students not taking that much physics might be more typical of the US than it is of India. Some of that has to do with availability of teachers and so on. What our basic principle is that all students should take physics, chemistry, and biology, and not sacrifice any one of them for the sake of the other. So the plan then is that right now in the US, 98% of students take biology, and 70% of students take chemistry, and only 36% take physics. So you see where our focus needs to be. Okay. In India, the situation might be different, because also the way the classes are structured are different. So they are not set up as year-long courses in high school, they're set up differently.
Then are you making that move? I think you mentioned that how you're changing the focus.
The flipping of.
Get physics first in and
yeah.
then get PCB.
Right. So some of the schools are going to it. they're flipping the sequence in which they're teaching it. There are district issues, there are district issues of when exams need to be taken and so on that come into it. But our point here has been, take physics in 9th grade. Doesn't matter if you take biology in 10th grade or chemistry in 10th grade. So the sequence of chemistry and biology seems not to matter quite as much, but having to take physics in 9th grade does matter, because you might never take it otherwise.
Ma'am, this classes takes, I want to know how long is the class duration for this to be implemented?
Okay, so fundamentally, this method takes a little longer to do than your lecture class. There's no question about that. So are you going to cover as many pages in your textbook? Probably not. But what you are going to gain is some depth in terms of what is understood, okay? In terms of just the class structure, the US classes are, sometimes they're structured as 50-minute classes and sometimes they're structured as 90-minute classes. So both methods seem to work.
In the Indian scenario where there are multiple subjects taught in the lower classes, so how would you like to implement this concept into the building up of the base?
Okay, so actually there is really not a particular problem with teaching physics over, instead of teaching it in one grade, in teaching it over 4 grades, let's say, but use the same methodology, okay? And as you perhaps go into teaching the 11th grade physics, using the same methodology, now you can use more math because the student has learned more math. So you can pick up the mathematics level in the higher grades. So there is not any problem with doing it that way. Yeah.
Yeah, I just have a small, in the Indian context, I mean, related to these questions which students are asking, have you, I mean, I can see that funding from NSF and HRD on your side. So is there any, do you know that is there any effort going on in India in this direction, number one? Or have you, let's say, about IIT people, administrations, did you talk to them? Or kind of something, some effort which you are doing as, you know, being there as a teacher, is it a possibility that the people in IITs seem to be the biggest institutes in India, faculty should go for such outreach programs under such institute funding, or was there any such talk with our people here?
Well, I would certainly be very interested in having such discussions, you know, and collaborating with anybody who would like to implement something like this in India. I personally haven't done it yet, but I would love to go that direction. It's, you know, it's sort of a new way of doing things, or a different way of doing things, and so it needs a certain amount of mentoring and help from I think, experts in the field, rather than just expecting teachers to pick it up and do it on their own. What we found is that in the school districts, teachers might be exposed to a lot of nice ideas, but the pressures of everyday teaching kind of get to them. And so it's hard for them to just implement stuff, cool stuff that they have learned. They need a fair amount of support as well.
Thank you, ma'am, for this very wonderful and insightful lecture. May I now invite our Dean IIR, Professor Nagarajan, to present you the memento.